Hello.
Hello.
Oh, we're trying.
We are recording. Welcome, everyone. My name is Jacqueline. This is our first meeting of 2021. Today's topic is on bearing lubrications and challenges. Our STLE members or executive are listed here. Myself, Jacqueline. Our vice chair is Pete. Kyle is past chair. Sarah is our treasurer. Program chair people, we have Clint, Ralph, and Yutong. Special projects is Ralph. Membership chairperson is Diane, and Calgary meeting coordinator is Maribel. We do have a few open positions. If anyone's interested and would like some more information, we'd love to answer those for you. Today's meeting, as I mentioned, is on bearing lubrication and challenges. Here is our list of our sites for our Alberta section. Please note we do have a LinkedIn site as well. If you'd like to follow us, please definitely go to that. Please confirm that you are muted during the presentation. If you have any questions, please note there is a chat and a Q&A option that can be found near the bottom of your screen. The members of the executive will be monitoring all questions and will either respond during the presentation or leave the questions till the end, and then we'll have Stephen answer at the end. Please note that this presentation is being recorded. So today's speaker is Stephen Yeung from NSK Canada. He holds a mechanical engineering degree that has 32 years experience in bearing industry. He possesses engineering and field application knowledge dealing with rolling bearings, linear motion products, lubrication, and vibration analysis. Today's topic, the presentation will cover bearing types, lubrication fundamentals, case studies on lube-related bearing failures, and tips to improve bearing reliability. So I'd like to welcome Stephen, and I'm going to hand this over to him. Stephen, you should be able to take control of the screen now.
All right, thank you, and I hope you can hear me as well. So I'm just going to share screen, and
currently I can hear you.
Hopefully, here we go. All right.
We can see it.
Okay, so. Okay, so thanks for the introduction. Once again, my name is Stephen Yeung. I work as a field service application engineer for NSK for Western Canada. My home base is Calgary. Today's topic, as mentioned, is on bearing lubrication. And before we get started, for those who may not know who NSK is, I just got a one-page slide on the company. NSK, it stands for Nippon Seiko KK. Literally means Japan Success. It's a share public-owned company. It's been it's based on home office globally. Global office headquarters in Tokyo. It was founded in 1916, so just over 100 years old. As you can see, it has 65 manufacturing plants producing bearings, related product in 13 countries. Sales company or offices in 123 in 29 countries. More importantly, from a technical standpoint, it has 14 tech centers scattered in 9 different countries to support all the sales activities. Today's number of employees is about 31,000. So NSK is one of the top, if I can call it top 3 manufacturing company for bearings. And in Japan, it is one of the largest for that country. as far as what they do, obviously, they have three major divisions. One is the industrial machinery bearings. I call it industrial division. That's where I belongs to. So globally, 23 of their efforts goes into that area, but even a bigger piece of a pie, 69% of the company's sales and efforts go into automotive bearings and components. And then the rest is under precision machinery and parts. Those familiar with linear motion product, particular ball screws and linear guides, and mechatronic products are all under that particular division. It's about 5% of the company's sales. So this is just a quick description, snapshot of the company. So today, I will be talking about, it's a general discussion on bearings, the bearing types, the ones with rolling elements, whether it's a ball or rollers, and it's for industrial applications. That's where I belongs to. The discussion will focus on a few things. One is I want to talk about some of the bearing basic, particular steel material and precision grades, because for some special applications, we have to basically switch steel material or even precision grades to cope with the demand. And a bigger focus of today's discussion is on lubrication selection from the bearings perspective. And one of the key primary concern is the oil film. And I'll be talking about that. And at the end, I like to go through a few cases where oil film consideration might not be enough. And it really poses some challenges, and you have to think outside of the oil film and into other factors. So let's start from the beginning. For rolling elements bearings, as you can see, it's manufactured in different types and sizes. Sizes as small as a pencil tip in a few millimeters in diameter, or as big as someone bearing using a steel mill or a ship loader, or a mining application. They are as big as 15 feet in diameter, for example, slewing ring. Their operating conditions, as you can imagine, the speeds, the loads, temperatures, environments, all different. As an example, if you can look at an axle box bearing that is used in a high-speed train today that is running over 300 kilometers per hour, where reliability extremely important, and the conditions there is drastically different than if you're looking at a dental drill that you visit your dentist once in a while. Today's dental drill bearings, there are two of them in there. They are very special. They are running as high as 400,000 RPM and have been made to a way that little to no vibration, and it's self-lubricated in a way is once the bearing has been installed, you don't touch it for a definite length of time. And consider bearing used in the steel mills. As you can see, the environment, heavy load, shock load, slower running, but you can see all the moisture contaminants that can pass through the seals into the bearing. So conditions in these examples suggested that the lubrication selections, when we look at them, are really based on the application itself. So often people ask, what's the best grease for the bearing? and that's not really a true as far as a valid question, because again, lubrication really should be selected based on what the bearing is being used in particular application. So a little bit information on bearing basic. Um, Bearings are made in have certain standard specifications. So I'm just going to talk about the steel material and precision grade before we talk about the lubrication again. In terms of bearing steel, what are the characteristics? The bearing steel have to be made with very pure and low in impurities or dirt components to ensure that it has good fatigue strength. The bearing steel should have very high hardness. Today's hardness values is about 5862 Rockwell C as the standard range for most bearings. High wear resistance, high dimensional stability. Normal bearing could be up to 120 C, but some bearings are made up to 200 degrees Celsius, and then high mechanical strength. Typically, there are common steel out there, and the most common is the through hardened steel that people might hear from time to time. Through hardened steel indicated through the cross section. The hardness remains the same throughout. So the recipe is under 52100. That's the ASTM so-called the spec. NSK is under Japan, the Japan industrial standard. So is the equivalent is a SUJ2, SUJ3. And the characteristic is the bearing is basically it's a high carbon chromium steel. You can see about 1% carbon, and then it's got chrome in there, and then with additional alloys. And the other one is a case carbide steel, and is again is opposite to the through hardened steel. The carbon is a low carbon steel, is about 0.2%, and then it's chromium, and then with different alloys added as well. There are many others out there. The ones for the aircraft applications, we use the M50. As you can see, the recipes again changes. They're different. And stainless steel often used in food industry, medical industry, for small size bearings. And again, stainless steel, as you can see, 1% carbon and got very high chromium content. So all these are produced, and there are many others for bearing that are used for different applications. But one thing for sure, bearings still have to be clean. They are very pure. For over the last 40 years, manufacture of bearing steel has been refined so much. The oxygen content has been kept so low. Nowadays in the year of 2000, NSK, as far as the steel goes, they maintain what they call the Z level. It's they can keep the oxygen content way under the 9 ppm marks. So in any case, for some of the key major manufacturers of bearings, try to keep the steel as clean as possible is one of the major goals in order for the bearing to have good fatigue strength. The other basic fundamental aspect of bearing is the precision grades. This table shows bearings that could be made in different precision grades, from normal to high, which is more precise. This is just a cross equivalent table showing different standard, which is the ISO, International Standard, GIS, this is the Japanese industry standard, and then the ABMA is the American standard. most bearings are made under normal precision or P0 or 8-1. That's for the so-called the standard bearings that you deal with on a daily basis. When the conditions gets a little bit more demanding towards much higher speed or higher accuracy, and we then have to go for something towards the right hand side, whether it's the 8-7 or P4 spec, the equivalent. We have to go for something with even tighter tolerance or better run out in order to achieve the objectives. So having mentioned these two things, just a little summary is not all bearings are made equal. Bearings have to be made differently in order to cope with the conditions that I mentioned earlier. Even back to the first slide, bearing that I use in a dental drill, these bearings are not everyday bearing. They are totally different than what you deal with every day. So the whole bearing has been gutted from the material to the cage to the ball material and the lubricant itself. So to meet different application requirements, sometimes the bearing design have to be adjusted. As I said, the steel material or precision accuracy are just two of the features that I just mentioned, and there are others, which is I'm not going to get into today because it's the time constraint. What about lubrication for all these different type of bearings? How do we look at them and how do we select them? For all bearing applications, obviously, when we look at lubrication selection, our primary concern is the oil film. As you can see, if the oil film is not there, you're going to have metal wear. So we want to try to establish an oil film so that metal wear can be eliminated or prevented. So, and that's really what the objective is for having lubrication is to form a film between the bearing components that move relative to one another so that metal contact can be eliminated. So, but the film has to be thick enough, but you don't want it to be too thick, which I will explain later on. It has to be able to maintain its thickness under different conditions, heavy load, shock load, high temperature. So they have to be selected in such a way that we can form a film adequately. So when we look at the contact area closer in a bearing, obviously, theoretically, we use the term oil film parameters, which is as a function of the oil film thickness versus the average roughness of the surfaces. So as you can see, we want the oil film parameters to be greater than 1 in order to have that separation. And typically we said, how thick is that oil film? We normally use the figure 1 micron under the operating conditions. So as you can imagine, the surface roughness actually is about 0.1, 0.2 micron. But to further understand explain the effect of oil film, maybe we can look at the strike back curve. That will help to kind of have a better understanding. So strike back curve, I would imagine most people have seen it, understand it. On the left-hand side, we have the friction factor, and then which is the y-axis. And on the x-axis, we have it's a function of the oil viscosity and the velocity and load. So as you can see, both the oil viscosity and the velocity, the speed of the bearing, for example, has a great impact on whether the oil film can be generated effectively. So when you look at the graph, there are 3 conditions. Boundary lubrications on the left-hand side, where the friction is very high. of course, that's the situation when the oil film is basically doesn't exist or very thin, and it cannot protect the bearing surfaces. And reasons for that is either the selection of the oil film was not adequate, or the velocity is not there. For applications that runs about less than say 5 RPM, naturally you are in a boundary lubrication conditions, and it's not much you can do except you're expecting the bearing wear to start from the get-go. But as conditions get better, maybe the velocity, viscosity becomes higher, a thicker oil film, or the velocity is higher, the oil film becomes thicker. And at that time, obviously the friction drops, and to a point is going back up again as the oil film becomes too thick, or increasingly thicker. Um, for the bearing perspective, we try to aim at this green box, which is under the refer as electro-hydrodynamic lubrication conditions. There where we can optimize the oil film, have minimum heat generations, but have enough oil film that it can prevent metal-to-metal contact, and to separate the surfaces, and at the same time generate the lowest heat possible. I mentioned earlier, as the oil film getting thicker and thicker, it might not be a good thing in some application. The thicker the oil film, what that means is you're gonna generate some unnecessary shear energy or shear stress within the lubricant itself. It's like running inside a swimming pool. The faster it runs, obviously, the more friction generated. So the temperature naturally will increase. And for bearing, that's not really very desirable in some application. So in any case, the green area is what we try to basically aim at, and try to optimize the oil film and making sure the oil film is adequate for the bearing application under different conditions. So how do we calculate that oil film, and how do we know the oil film is good in certain application? I use this watercraft, which I dealt with some years ago. And underneath the watercraft, there's a pump, and there are two bearings that's very special, somewhat custom made for that application. It is a double roll ball with a bore size of 45 ID and then 61 OD. The speed is 7,800 RPM. If you kind of understand what I said earlier, the speed is a big factor. So right from the get-go, I know 7,800. I know the oil film is going to be created, but I'm just afraid maybe the oil film is too thick. That's one thing I needed to check. They're using a 46 weight grease with a base oil about 48 Stokes. The recorded bearing temperature was 55 degrees Celsius. So that's not a bad temperature at all for bearings. Anything under 70 degrees, it's considered to be a good number for so-called bearing used in general industry. So how do we check it? Very simple. My first step is to calculate the minimum oil viscosity at the operating temperature based on the application requirements. In this case, namely the speed and the bearing size. And secondly, I will calculate the oil viscosity at operating temperature based on the lubricant used. All right. So normally we just input it in our in-house program and it will spit out the results. But here we're just gonna do it by hand. Here's a diagram that we can make use of to calculate so-called the minimum required viscosity based on the application requirements. So on the bottom, we have the size of the bearing. In this case, the mean diameter is 53. And then the slanted is the speed of the bearing. So basically, we just draw a line vertically up and hit 7,800. And then go across horizontally. And it tells me that for this application, 7,800 RPM, I need minimum 7 centistokes at the operating temperature. In this case, is 55 degrees Celsius. So I made use of another graph basically, and then looking at 55 degrees centigrade at 7 based on 7 centistokes. You can see I actually need something really thin to and be satisfied with the oil film conditions. So, but let's look at, they're using a 46, and based on that, using a 46 weight at 53, basically at that point it's about 25 centistokes. So when I do the calculations, which is the viscosity index, I got about 25 over 7 is 3.5. As I mentioned earlier, under the oil film parameters, and that little green box, I'm looking for somewhere between 1 to 4. That would optimize basically my selection. So in this case, 3.5, I think is very good because they're not really, the lubricant is not an overkill as far as the viscosity is concerned. That's why the temperature was able to maintain at 55. And so from that perspective, the selection was quite adequate from the oil film standpoint. Oil film selection is our primary concern, but it is not the only concern. When we look at to select a lubricant, the quality of grease and oil, depending on the types, the type of base oil, the thickener type, because it has so many functions, the use of additives, depending on the application, consistency, temperature limits. These are all important factors and must be considered along with the oil film in order to come up with a proper selection. And obviously, because it is for a bearing, the bearing design parameters such as the speed and load ratings, that also need to be satisfied as well. All right. So they are, I refer as the standard industrial rotating equipment, such as electric motors, pumps, industrial fan and blowers. There are a lot of equipment similar to this out there. Their speeds are moderate to high. The conditions are quite predictable, and because there are speeds involved, so the oil film often is not really a big concern. And for these equipment, normally if I have to select a grease or oil for it, a base oil viscosity between 68 to 220 at 40 degrees C are generally very good enough to get that oil film established for the bearings. And because of that, normally EP additives like anti-wear and EP are not really needed because the oil film is there to separate the rolling surfaces. All right. But having said that, there are certain applications out there provide some additional challenges, and in those situations, we need to consider some additional factors other than oil film. In fact, sometimes oil film itself won't do anything because the situation is so different than the norm. So I'm just going to go through a few applications and just to illustrate that, again, not bearings are made equally and not applications are the same. there are cases where the speed is extremely slow. There are cases where the speed is, I refer as too high. Bearing sometimes used in very wet condition. And the last one is cases where involve very extreme corrosion and contaminations. So under these situations, sometimes we can look at the oil film, but sometimes it's just there are more to it. So let's look at the first case. This is, and I worked many years in the steel industry, involving in that area. And one of the very typical applications is the slab caster, where they produce the steel slab. Bearing rotational speed is 2 to 5 RPM. That's very typical. The problem is extreme slow speed and heavy load. The mill like to use just a grease with low viscosity due to cost and pumpability. The main purpose of using the lubricant is to flush out contaminants and moisture. So because of that situations, what can you really do? When you look at how bearings are being the result of the condition, typically a heavy duty roller bearing, double roll bearings are being used. You can see heavy load, extreme slow speed are the two primary concern for the bearing. And there's going to be intrusion of scale and water entering into the bearing, and also high temperature at times. So right from the get-go, the bearing was subject to wear. And for this type of bearings, the wear will take place over a long period of time, and then flaking will gradually develop. If the bearing can be removed or replaced prior, at that point, that is perfectly fine, because it doesn't shut down the production. But if flaking could further develop into fracture, and once the bearings start to break apart, then obviously the roll will not able to rotate anymore. And that's where the problem and people try to avoid. But with such a low speed, and if you try to look at the oil film, it's similar to what I was doing earlier, looking at the bearing size, and then looking at the speed of that bearing. And then if you go across at operating temperatures, you're looking for a lubricant grease that is close to 2000 centistokes. And when you try to factor into the operating temperature at 85, you are looking for something that may not be commercially available. You're not gonna look for something that is super heavy, because it becomes not practical to be used in this application. So this is what I said about oil film. And sometimes even if you want to provide something with the adequate oil film conditions, maybe there are cases that you just cannot, mainly because the speed is such a low speed. So when you do that viscosity ratio, you basically have less than 1, so you're in a boundary lubrication condition right from the get-go. So as a summary, due to extreme slow speed and a lack of oil film, one can expect the wear process to continue right from the get-go. And to prolong bearing service life, in this particular applications, I would consider these factors. I would try to eliminate contamination, scale, and water as a constant on a constant basis. Supply and maintain a constant supply of lubricant to the bearing, even if it's less ideal. try to use a lubricant with the lower viscosity, which most mill would do, but sometimes they just use a straight low viscosity grease and not consider the anti-wear additives. And I think that's where the anti-wear additives or EP additives would become beneficial. And then the other one is to use bearing with special material to improve the wear conditions in the bearing and to prolong the bearing life. But I wouldn't really think about using bearing steel unless the first two conditions are satisfied. You have a stable condition, then you can see the gain in terms of using better steel material. So that's my case number two. The case number one for case number two is the speed is too high. Typically, in my past few years, I guess, there's a few applications. The bearings actually are needed to run above what we refer as the speed rating. In this particular application, it's a vertical arbor gang saw with it's almost like a spindle with two bearings. A 6228 is a ball bearing, and the operating speed is 3,400 RPM. So, but when you look at the catalog, the older catalog, the speed rating for grease is only 2,200. And then for oil, it's only 2,800. How can that be possible? So the future speed, as we know, not only 3,400, they're pushing towards 4,000 RPM. So what can we do about this? In order to cope with the higher running speeds, in this particular case, we eliminate grease. We're using oil-air lubrication. The selection originally was 68, but as speed increases, we know generate that oil film is not a problem. Generate too thick an oil film could be a concern. So that can be go to a 46 weight or 32 towards the future. And the bearing with a higher precision grade, we can push for another 10% increase in speed capability can also be considered. So for some high speed applications, again, we're not just looking at the oil film or the lubricant. We then have to look at the methods for lubricating the bearing in order to cope with the conditions. And in this particular case, not just the method, but also the bearing precision grade and have to be kind of put in context. So in the future, when they go to 4,000 RPM, we can still able to maintain the bearing performance. And at this point, just want to point out the speed rating in the bearing catalog. I'm using another bearing as an example. So in the older catalog, you always can see when you look for speed information, there are two pieces of information, limiting speed under grease or oil. As you can see, if you pick the first bearing, it's 1,100 and 1,400 respectively. These are conventional speed definitions. And what that means is if you run the bearing under certain load conditions, as long as you run within this limit, then the bearing will not seize. But when you look for a newer catalog, you'll see updated speed definitions have been put in under thermal reference speed and under mechanical limiting speed. And there's also the grease information as well. You can see the grease information remains the same, but there are new informations indicated that with, for example, under thermal reference speed, it's 1,400, 2,400, and under mechanical speed, it's 2,600. So when you look at under these definitions, 2,600 versus 1,400, you can actually operate the speed over almost like 100% increase. And why is that? Because under the mechanical limiting speed, for example, that means if you use a system that can provide efficient heat removal. And if it's a more efficient system, such as air oil, you actually can achieve a much higher number than if you look at and compare to conventional oil rating, which is based on dust and oil bath. And so if you look back to that example number 2, so that's why the speed could be pushed. But obviously, another big factor was loading, which I haven't really talked about. And, if the loading is on the heavy side, be very careful with this definition. So I just want to bring you to the attention is when you read the information, try to understand what it means and what is implied, but they're not really a definite number. I would just use those, everything as just a reference, for reference only. So just additional notes, if you want to push bearing to run for higher speeds, as I said, you can look at oil film for the lubricant and consider, but there are additional factors you need to think about. The lubrication method, because grease being the slowest and oil bath, air oil, oil air system, oil mist system certainly provide some advantage in that area. The oil viscosity as speeds goes higher, then may need to get adjusted. The bearing precision help to push for higher speed, and sometimes the material need to be changed as well. I haven't talked about bearing internal clearance or preload, which help to control possible ball rotor skidding or rigidity issues. But again, this is something, and also the shaft and housing fit tolerances. All these factors have an effect on bearing oil film conditions and temperature. So it is not a simple task when somebody just wants to push for higher speeds. And the third case that I thought was interesting over the years was wet conditions. The segment is food and beverage. If you walk into a chicken plant or potato chip plant or brewery, on a daily basis, regular wash down with high power, high pressure washer are taking place every 3 hours or so. And with that, obviously, grease sometimes get washed out, and in that case, causing corrosion to the bearing. And sometimes you have contaminants actually get inside. So based on that scenario, doesn't matter what lubricant you picked, if it doesn't stay in there, it's not good. So the idea is to, what do you do in those cases to prolong bearing life? And sometimes we have to think about out of the box per se, and look for unconventional lubricant. And this is one of the products that are being used in the food industry. Is under the name is motor oil, or people call it solid oil, to replace grease, because it stays within the bearing and it doesn't get washed out under high pressure. It's really the matrix consists of polyolefin, basically plastic, and then you have oil impregnated with oil, and and sometimes you can put them in naked bearings, and you can put them in a housing like this with the plastic housings and stainless steel inserts, and so you have a solution that is totally help to prolong the bearing life in this type of conditions. And sometimes the bearing to be used in the food and beverage industry have to be also stainless steel as well. And so in this particular case, obviously, it doesn't matter how you select the lubricant, because it doesn't really last and stay in one place. So there isn't much you can do except you got to think of something else that can solve the problem. And the last one I want to quickly go through is the extreme corrosion and contamination. And throughout my career, this is probably one of the worst. So it's a mud motor, and for those who work within the oil and gas industry, the the mud or the drilling fluids is pumped through the internal area so that it can operate the drill head. And unfortunately, all this drilling fluid has to pass through what they call through the bearing, and we use so-called, this is the stack bearing. There could be 6 of them or 8 of them. They are designed to take the load in both directions, and but again, because they're not lubricated by anything except the mud. So the mud could be oil-based and could be water-based, which is the most corrosive, and also come with solid particles. So based on that scenario, and the objective is you want something to put in, and unfortunately, it can be only lubricated by the drilling fluid, and you want something that can last, at least not break down during the production or the drilling. And so the only thing we want to avoid here is, and it's not a new application per se, and this has been around for a long time. We want to put something in there so that when they do the drilling, they will finish the production. Whatever runs they want to make, maybe 3 or 4 every time they go down the hole. And when they come back out, hopefully everything is in one piece. So the main factor in this case is the bearing internal design have to be well designed. Again, we put in special bearing steel material other than the conventional one in order to make sure that there's no fracture happening during the drilling procedure. So as you can see, this is what it looks like after the tools being retrieved and the bearings taken apart. Because it is a water-based drilling fluid, you can see the appearance doesn't look very nice. It's all rusted, both the balls and the rings, but nevertheless, there's no fracture. So as long as it can be guaranteed during drilling and the bearing doesn't break, and so the thing will cease to turn. So they are happy with the results. In this particular case, obviously they will replace the bearing and put a new set of bearing in, and for the next production run. So this is my last slide. Just to mention, there are many technology development within the bearing world. Because of the applications are more demanding, even today with the EV market in the automotive size, the motor, for example, no longer running at 1800, is looking for 30,000 RPM. As an example, but one of the area for heavy industry that NSK have done quite a lot over the past 20 years has been focusing on so-called the material technology. Bearing with special steel and special heat treat. So I don't want to go too much into the details, except, this particular slide shows 6 different formulations. The TL steel is for the paper mill in the dryer cylinder applications. For the UR treatment is for general industry for ball type bearings. That is for an application and bearings that look for higher reliability, longer life, and SWR is used in the oil and gas industry, like the mud motor, also the steel industry, where the speed is very slow. In the caster, for example, it's for higher wear resistance and fracture resistance. The STF, WTF are for the steel mills, the roll neck bearings, and the HTF is for the mining industry, such as the head pulley and the conveyors. Again, contamination is a problem, slurry pumps. So there are many so-called new technology and being employed, and just to deal with the increasing demand out in industry. And with that, that's basically is my last slide. So I basically just turn it back to the host. Can you hear me?
Yeah, we can hear you, Stephen.
Okay.
I think Jacqueline looks like she's frozen up here. Give me 1 second here. So we have a couple questions that came in through your presentation, and thank you, by the way. That was very informative. So there's 6 questions. The first one, does NSK have a manufacturing plant in Canada? If so, where, and how many plants in North America?
Oh, there's none in Canada. In fact, I think NSK never had a plant in Canada. In United States, there is I would say up to 3, a plant that makes mainly ball type bearings, 2, and then hub units, for example, and there's another plant that is focusing on linear motion product, such as a ball screw and some, I think under this precision product and parts, and I think that's about it. The rest is in the rest of the world, and as you know, for the past 5 years, it's still the majority is in Japan. But in Asia, for example, China, we have, I would imagine, 6 to 7 plants at this point. The rest is in Europe and UK. NSK bought RHP in the 70s. So if you remember that name in terms of machine tools, bearings, so a few factories are still being ran over there. So again, it's Poland, Brazil. It's, as I said, scattered quite a bit. All right.
Great. Okay, thank you. The next question was with regards to your first case study, application number 1. The question was, what was the chosen oil viscosity if the computed 2,000 centistokes wasn't practical?
Well, it ended up that every mill would use somewhere near 200 centistokes to be the norm because of the pumpability. And I have not seen one that uses 320. In fact, some mill was only using 100 centistokes and with no additives whatsoever. But now some of the lubricant, because of the thickener, it has the anti-Brunel properties. So it's been chosen. So there's a couple of product out there. I think over the years when I spend my time in Ontario, I mean, it's kept changing. But the ones is chosen is now is basically 220 centistokes. Consideration is into the thickener properties, and if not, the additional EP additives or anti-wear agent that is being employed within the product itself. Okay. Okay.
Thank you. Next question. Have you encountered a case when the sodium content in a lubricant affected the bearing life?
Sodium content means salt?
I'm not sure. Benji, if you want to confirm that in the chat box, if it's the soap thickener or if you're talking about a contaminant, but maybe let's assume it's the thickener type.
So the question is, okay, you have to repeat that question again.
Sure. So, yeah. So the question was, have you encountered a case when the sodium content in a lubricant affected the bearing life?
Sodium content. No, I don't recall. I'm not sure which industry. I mean, if I conclude that generally speaking is contaminants or things is corrosive that affect the bearing. I mean, throughout many years, there are many of them.
Sure.
But the thing is, whatever gets in there, one of the measurements is the the concentration, right, of the substance.
Sure.
How does it affect the lubricant itself? Even I mentioned stainless steel bearing, and sometimes even stainless steel bearings is also get corroded because of what's in the water. So
Gotcha.
yeah, so I don't know how I can answer that better unless I know the details.
Sure. No, fair enough. Moving on to the next one. Please comment further on mist oil versus oil bath.
Oh, oil mist, or I mentioned oil air in my slide. And oil air is slightly different than oil mist. In principle, they're a little bit different, but both systems compared to oil bath, definitely is a lot more efficient system, and it can, because there is airflow, particular oil mist. If you mention oil mist produce positive pressure within the housing, for example, that can help to protect bearing from contamination. And not only that, these are for because the amount of oil that you use is so low. It's for really for high speed applications. If it's one of the area where the oil mist and air oil can be used and take advantage of the efficiency. As you can see, the rating under oil bath is quite low than compared to the other rating that I mentioned, which is it could be double that amount if it used effectively.
Great, thank you. Next question, does NSK have a lab in Canada that analyzes failed bearings?
Oh, no, the way we analyze failed bearings are a field service guy like me will do the first initial inspection for our customer, and we have our major lab in Michigan, USA, has one of the most advanced tech center. It can basically look at from failure to material to lubricant, and also a research area. So if the way we deal with customers issues, if the local company cannot get it resolved, then we get support from them. But there's none in Canada because it is a sales unit. But in the States, it's a much bigger operation. So the research center is located in next to the head office, actually, Michigan.
Okay.
Ann Arbor, Michigan.
Great, thank you. Another question on molded bearings. Any further details? One, are they made in specific sizes? Two,
yeah, on the small one, NSK choose the word molded, means it's done by injection molding. So on the small bearings, they are injection molded, but on the larger bearings, they are basically, if I can describe it, the mixture is hand packed into the bearing cavity and then subject to a high temperature, just like baking a cake. But the size limit is based on the equipment. If I can use it as an oven, for example, how big of a bearing can it handle? And that's the limit to how big of a product you can put in there.
Okay. So the second question regarding molded bearings was, what is the average lifespan?
Yeah, that's a good question because first of all, you don't apply that to any applications. It is a problem solver. You only apply it because you understand what the application is and why the bearing life is shortened. And then you start thinking about why you should apply such a product. One of the area that you can apply it because, for example, places that hard to reach. And
Right.
and again, there's a limit to how fast the bearing can run with this product. And so it's a speed limitation, there's a temperature limitation. But if you compare to grease, it can hold more oil per volume than as compared to grease. All right.
Okay.
And but again, in a foot plant where if the bearing do get washed down and the grease come out, this bearing will probably last a month. But when you put in motor oil, sometimes you can have maybe 3 times the life, 4 times the life. But again,
Okay.
you have to factor in the production downtime and what really makes sense. To me, it's a problem solver. I do not want to offer that to anything without understanding why it's being chosen and not grease, for example.
Sure.
Right.
So the last part of that question regarding molded bearings was, can you comment if this is practical as a kiln trunnion bearing in a cement plant kiln?
Yeah, kiln, there's heat involved. You're talking about trunnion bearing then, I would imagine.
Yes.
We have not used it in the kiln unless again, there's a temperature limit, but again, depends on what oil is put in. I think the bearing being using grease, yeah, it is slow enough. We do have molded oil product put in larger bearings. This is right now is not, I haven't seen one put into that application. But again, I need to know the details because we do set some limits as to what is the temperature. But again,
Sure.
if the grease product is exhausted in terms of selection and is still getting short life, we need to find out what happened, what is the reason before I would jump into the motor oil, right? So,
Sure.
but again, if there's more interest in from the person who's he can contact me directly, and then we
Okay.
can discuss a little bit further on this application.
Okay. Have you encountered electrical fluting bearing failures on electric motors?
Yes.
If so, please provide some ideas on how to address them.
No, that's a common issue, especially today with the VFD, where there's going to be a buildup of voltage. Electrical current damage is it's common, but I know end users basically try to eliminate that as much as possible. Obviously, the bearing company would have bearing made in such a way that it would deflect the current from going through the bearing with the ceramic coating, for example. If, for example, the high-speed train in Japan, all traction motor bearings would have ceramic coating on the OD as a precautionary measure. But obviously, out in the industrial world, there are devices or different ways to deflect the current from passing through the bearing. So there are, I think, some kind of rings that they put in, but the end of the day is if there's an issue, they need to know where the source is and then try to resolve it that way. But again, I need to know the specific, but electrical damage through motors, once it happened once, I think most people can trace it back as to what and where the source is, and they could kind of fix it that way or eliminate the source if they can help it. But VFD is something else they might not be able to do because if the mechanical side, electrical side don't talk to each other, the buildup will be there eventually. But again, whether you use a bearing with a different material or you try to find ways to deflect the current from going through the bearing, there are different ways of doing it. All right.
Sure. So going back to that original question with regards to sodium and the grease, The question said that a customer sent in a grease sample to a lab and found sodium in the sample. Apparently it wasn't measured as a QA spec for that grease. Another bearing supplier stated that in specific cases, sodium is detrimental to bearing life. Another one said he did not encounter it as a contaminant.
I think the question is does the sodium really has affected the lubricant itself? And as a result of that, the lubricant became less effective when it's being used within the bearing. Again, that's back to does it affect the oil film? And if the concentration is too high, everything is too high, then obviously there's going to be some effect on the lubricant film, and perhaps I don't know if the sodium is in the liquid form. It's just put it this way: the oil film is only 1 micron. We tell people sometimes don't expect hard material will do damage. Softer material than steel can also do the same damage. So, but I say if it's in a liquid form, is how has it really affected the lubricant first, i.e. the oil film conditions. And but sometimes your calculation might be good, but in practical side of things, it might dilute the lubricant, and then everything gets thinned out. You will still have the problem. The oil film condition is good because it's all theoretical, but as I go through some examples, the real life doesn't work like that at times. And, yeah.
Thank you. Another question here, does NSK have any experience with pellet mill applications used in the biomass industry? If so, what is the ideal base oil viscosity for the grease in these applications?
Oh, which application in the biomass industry?
Yeah, in a pellet mill.
Oh, we have bearing supply to the pellet mill, but they have to be specific. I mean, we'll go back down to how do we select lubricant, right? We're looking at the running speed. We're looking at the bearing size. We select the oil film conditions, and then depending on what bearing types are being applied to it, and then we select the bearing and lubrication accordingly. And I listed earlier, oil film conditions is a primary concern, but it's not the only concern.
Right.
What about, can it be used with grease or an oil bath, or does it have to be a better system to cope with the conditions? So the end of the day is, I also said you need to look at the bearing itself, look at the rating. Is it really suited for this application? So, but again, perhaps it's too generic for me to address that question. So, sorry.
Okay. No, that's good. Thank you. Okay, so going back to the molded bearings, asking if it's more of a solid lubricant in a bearing form.
It's solid, and how it works is when it starts to rotate, because of friction, it helps to release the oil, and that oil then zip out and then just cover the whirling surfaces, and that's how it works. As I said, there's a limit to how fast it can run, but again, people do put in different type of oil, low temp oil, synthetic oil, mineral oil, that enhance the so-called the temperature range of the product. But like everything else, the original intent for this product are for slow moving application. And I can use an example like an overhead crane in a plant where there are wheels out there to move that big crane in a big factory. No one wants to go up there and lubricate that bearing, but that bearing is running, it's a roller bearing, they're running very slowly. But once you put the motor oil in there, basically, you can leave there for a super long time. Okay.
Great. Another one. So they keep coming in here. It's pretty popular, Steve. What can be done to extend the life for a bearing lubricated by oil which is experiencing ethane dilution. Oil viscosity is changing in a natural gas compressor. I assume a screw compressor.
Oh, that's a very specific area. Well, I think the time there are specific lubricant if it's a wet compressor, twin screw compressors, and there are specific I think lubricant selected for them. But they aren't they mostly injected in there? They are
Right. Yeah. That's right. Yeah.
Yeah. So back to the question again. What is it they want
yeah,
to?
So what can be done to extend the life of a bearing in that application?
Well, I mean, the lubricant there is to lubricate the bearing and screw, and one of the problem is you want to avoid contaminants. But if the contaminants can be avoided, I think based on I only dealt with maybe a few key a few times, and I think contaminations, and then people do on a regular basis do oil analysis, and just to make sure that nothing abnormal is going on, and with the proper selection of the lubricant for the gear and also the teeth and also for the bearing. I think that's I guess the only way. But if you really look into the details and see whether, again, I can comment on, I did point it out, the quality of oil is a factor, but that's really beyond my reach. But I know,
Sure.
like bearings, not all oil products are made equally. So one have to be really look at what's out there for the same application, right?
For sure. Okay, no, thank you. And then Marius, to your question, there's different base oil types that can manage gas dilution differently. So to add to that, well, there's a question about. Go ahead.
No, this because I don't specifically work in the oil and gas industry, so some people out there probably have a lot more knowledge than me. I basically see myself to be a generalist because I touch everything.
Sure,
but
no problem.
Some area, yeah. So.
Next question comes in asking if you're willing to share your email address.
Oh, for sure. I think Jacqueline can have my email address, right?
Yeah, we definitely have that. So we can,
for sure.
We can share that.
Sure.
Sure. Okay, great. Okay, so going back to some of the electric motors again, where they've used EP grease, lithium complex greases or lithium-based greases in the motor bearing as specified on the nameplate in Siemens electric motors. So the question is, EP equals corrosive, question mark.
Oh, extreme pressure. But as I said earlier, you have speed for electric motor bearings. There are, whether it's the 900, 1800, 1200, 3600. Nowadays, even worse with EV. Motors for EV is extremely crazy. Is the speed is even higher, go higher and higher. So traditional electric motors, I don't see the need for EP. Because most of the grease associated with EP are in the neighborhood of ISO VG 220. And sometimes I feel they're a little bit too viscous. And a lot of them can lower to like 100 centistokes, ISO VG 100, which is, there's a lot of grease out there is in that category, still under all-purpose grease. And I mean, even the Polyrax EM is in that neighborhood, except it is a complex grease, so the temperature range is higher. But I don't normally recommend EP. I just don't think it's needed. So for the motor
Okay.
application.
Thank you. Please discuss the importance of the quantity of lubricant in a bearing.
Oh, that drastically changes from one type to the other. For normal bearings, initial packing is full, and soon later the bearing will push out the stuff it doesn't need. And then you go through that temperature increase, and then the temperature gradients will lower to a steady state. And so we have this so-called a run-in phase for most general applications. Again, I don't worry about them because the speed is not so extreme. But if you are dealing with anything like machine tools bearings, anything with higher speed, I have to be very careful with what I'm doing. For machine tools bearing, for example, with high precision that I mentioned earlier, you cannot afford to pack those bearings from the get-go because these bearings will be overheated right from the beginning. So I would just say for everyday bearings, the practice is one thing, but for higher speed, high precision bearings, we call it super precision bearings. For machine tools, as an example, they have to be handled quite differently. And
Okay.
all right.
Okay, thank you. This looks to be like the last question coming up here. With regards to automotive bearings, what is the best sealed for life lubricant type for wheel bearings?
Oh, I can only comment. The automotive bearings, like a hub bearing, the seals are designed differently. They are a lot more complicated. They're a lot more sturdy. They do not look like the ones that you buy like a ball bearing, because they are, if it's a hub bearing, they are supposed to be sealed for life. That means is no maintenance is required, so the seal have to be very tough design wise in order to protect the bearing from environment. I can't comment on that with too much information, or I can tell you their design is a lot more complicated. And not only that, off-road equipment, hub bearing, for example, the Argo, if I use that, people go out hunting and the bearing have to go through, swim in the water per se. Like imagine those seals are also kind of special. So yeah, I can't talk too much about, except it's designed in such a way that it guarantees for certain kilometers. And they are a little bit different and a lot more sturdier and complicated compared to our everyday ball bearing that you see. All right.
Okay, and then the second part to that question is, are high performance electric car wheel bearings different than conventional vehicle wheel bearings?
Oh, that I haven't gone into that yet. I mean, I only get my knowledge is because it's their development, and I don't really work in that area. But I do get my nose into the electric motors and see what's out there. But I can't comment on the wheels. I can comment on the motors though.
Okay, another one popped in here. What are the considerations when you switch from a ball to a roller type bearing in an application?
Oh, you don't do that under normal circumstances, because when you change from ball to roller, you are gaining a lot of load rating or capacity, but losing a lot of speed capability. So normally we don't, when simple have to switch, that means the original selection had a big problem. So we have to really consider what's happening. But use electric motors though, as an example. A lot of electric motors, it's set up in a way it's a direct drive. But sometimes if some end user decided that he wants to put a belt at the output, and that will put a lot more load on the outboard bearing, and that's the time I would say you have to consider probably switch from a ball to a roller type. But that's a very I've seen that a few times over the years. If you don't do that, the belt will put so much load onto it. But as a general recommendation, yeah, it's not something I would easily would say go ahead and do it, because you have to kind of
Okay.
study around.
Excellent. Well, that wraps up the questions that we had in the Q&A box. Jacqueline, are you back on?
No, still frozen.
No,
So
still frozen.
yeah, I don't know if somebody wants my email. I don't know if you can help to send it out, Clint, and just to, I'm not sure.
Yeah, no, for sure. There'll be a recording of this webinar as well, and we can include
Okay.
your email address on that as well.
Oh,
there we go.
Seriously? Finally?
Yeah, you're back.
Yes. We have your email and I will forward it on. If anyone requires it, please just send a message over to the Alberta section and we will definitely get you in contact with Stephen. Did we cover all the questions, Clint?
Yeah, we've gone through it all.
Perfect.
Lots of questions
Thank you again,
today.
Stephen. And thank you everyone for joining. Have a great day and we'll talk to you next month.
okay. Thank you.
Thanks, Stephen.
Okay.
Take care.
Bye-bye.